let's start today's talk. Today 我想听的中文，我先讲中文好了。反正待会数位性馆长会当全程翻译。好，那我先介绍今天的贵宾，好吧？今天的贵宾，首先我们邀请的 speaker 就是Jane Luu，welcome。还有我们著名的科博馆孙维新馆长，我们欢迎他。还有科博馆的科教组的助研究员王博士。上个礼拜是我们的翻译者，那今天改由孙馆长。那再来，我们还有其他来的贵宾清华大学赖思平赖教授，还有远从日本Weekend 来的Ishibashi Professor。那还有3位系主任哈，那首先介绍陈继天陈主任，那艺术系黄宏汉黄主任，再来是物理系何梦书何主任。那因为在座很多贵宾，我就不再一一介绍有些师长在。那上个礼拜那个David Jewitt 有给一个 talk 关于那个所谓的这个古柏带的一个发现，但是他后来留下一个伏笔就是今天我可以 continue， 就是说这个红帽上礼拜有听演讲的举手，上礼拜有听的那有些 question 大家可以看看到底是我们这个 Professor Luu 他如果来帮我们解答他的这个问题，那我做简单的一个介绍那Jane Luu是一个他是1975年他移民到美国是一个越南美国籍那后来他的大学是念斯坦福大学，那后来在麻省理工以及伯克莱完成他的学位，然后目前在 MIT 的那个 Lincoln Laboratory 的服务。那他得到一些相当多优秀的奖。最有名的奖就是 Annie Carner Award 还有那个 Astronomy Shell Prize， 在1991就得到对不起，2012年就得到了，还有一个 Covey Prize 2016。那他同时跟因为他发现了他跟那个上礼拜的演讲者 David Jewitt 在95年的时候。经过5年的发现，那发现那个所谓的 hyperbill 的一些实体，一些星体，还有它的最大的moon 月亮叫做Charon 这个星球。那它这个星球后来他们取名叫做 Smiley。这个星球，那它的在天文学的贡献相当大那也有可能就是他现在很年轻，所以说将来他继续几年，他有可能就是我们的就是所谓的诺贝尔的，因为已经得到了一个塞勒夫奖，就是东方诺贝尔奖。那他的天文学的贡献，相信会影响继续影响到一些私人的发展。那我不多说了我们就首先来鼓掌欢迎Jane Luu的 lecture。那个我们先请孙馆长来先给他介绍。
谢谢。 兴能感谢施院长。我们特别要强调的是，这一次不好意思啊，大家千万不要误会，不是在帮科博馆做植入性行销啊。但是呢，我们就是因为在今年6月底，我自己做了一个展览，策展。因为过去20年呢，天文学家在太阳系的研究上做出了许多突飞猛进的重大贡献，但这些重要的贡献一直没有落实在我们的教科书里面跟社会大众的了解里面。我看着实在很着急，就干脆就自己做一个展览。馆长要做展览最简单，因为没有人会反对。我们从6月底开始呢，就一个漫步太阳系的特展啊，我请每个人拿一本笔记本出来给大家看一下啊，我们就。像这样，这个展览我觉得很有趣，因为它是一个艺术展，那包装的是科学的内容。当然，我们还有一个非常漂亮、里面充满知识性的笔记本哈，待会儿我们要送给问最佳问题的人，好吧？但是很重要的一点是，我们刚好在过去400年里面，对太阳系研究有重大发现的11位科学家，在我们展场里面的高墙上面，那里面有3位是现代科学家。就包含了刚刚施院长讲的那个Dr. David Jewitt， 还有今天的 Dr. Jane Luu 刘立信博士，他们是师生，当年在 MIT 麻省理工学院的师生，共同在1992年做出一个重要发现，就是发现了第一个海王星轨道以外的古柏带天体。从此以后，对古柏带天体的了解就如水银泻地，一发不可收拾。在那边发现成千上万的小天体，彻底改变了我们对整个太阳系的认识。上礼拜我相信David Jewitt的演讲对大家很有启发了。那这礼拜呢 Jane 也会，他从另外一个角度谈另外一个天体，但都是太阳系里面的小天体。哇，这是从太阳系外面来的，蛮有趣的啊。那我们希望进行的方式，也就是 Jane talk about the section 讲一部分，然后我们停一下，我跟大家讲讲，用中文介绍一下里面主要的主旨，因为天文毕竟还是有一些专有名词的，好不好？希望这样不要打搅大家，但至少让大家理解的程度比较高一些。但是 Jane 除了科学之外，他本身也是有一个坎坷经历的。他是1975年从越南逃出来的人，他的父亲是当年美军在越南的翻译，所以当越共掌握了整个越南，他的父亲绝对不可能留在越南，所以是1975年逃到美国去的。但到了美国以后，就念书，开始喜欢上科学。今天早上在这边录影，他非常鼓励男孩子、女孩子去念科学。他说男孩子比较有自信，女孩子缺乏自信，但是都应该好好念物理跟科学，很有意思。好，那我们就先开始做。很谢谢这次中兴大学主要来支持这几个演讲者，很高兴。好，谢谢。
So I'll stop my talk, but when you have to stop me and explain, just let me know and I'll stop. Okay, so if you follow the news at all in the last 2 decades, you probably know that the last 2 decades have taught us that stars have lots and lots of planets. And so this is a plot showing most of the stars, most of the exoplanets that have been found over in the last 2 decades. Most of them were found by this spacecraft, the Kepler mission. You probably heard of that. So the blue one was found by observers on the ground, and then others after Kepler. But the yellow ones, these are all the exoplanets that are discovered by the Kepler mission. So as of last year, we found about 3,500 exoplanets, and Kepler found about 2,500. And these exoplanets come in all different sizes. The ones down here, that means they're about the size of Earth. The ones here, about the size of Neptune. And the ones here, about the size of Jupiter. Right? And this x-axis shows you how long it takes the planets to go around their stars. So the one over here takes 1 day to go around. Over here takes about 10 days, 100 days, and 1,000 days. So these are most of the exoplanets that we have found. Again, they come in all different sizes, and most of them were discovered by the mission Kepler. So in just 2 decades, we went from the situation where we thought maybe exoplanet existed to now where we know that there are more exoplanets in our galaxy than there are stars. So that's a long way.
Okay, Jane, welcome back to the lounge.
Okay.
大家看到这个图其实非常重要。刚刚讲了过去20年对系外行星的发现，也是在别的恒星旁边的行星进展非常快。 左边那个数字告诉你说，现在确认的系外行星有3500个，但是呢，由克卜勒天文任务所发现就达到了2500个。金黄色的是克卜勒那个任务，2009年上天去的啊，做了观测。右边那个很重要，是地球、海王星跟木星的大小。所以呢，你看横的比过去就知道，有许多系外行星是跟地球差不多大小的。那底下是转动周期啊，公转周期有1天、10天、100天、1000天的。所以大家好奇就是跟地球大小的，然后转动300-400天的，就会跟地球很接近的。但重点是他刚讲了一句话说，过去的20年之前的人想说，别的恒星旁边可能有行星吧，经过20年的努力，现在知道，银河里面所有的系外行星数量远超过恒星，所以这是一个非常大的进展。
So the Kepler mission, so this just shows you the various satellites, space telescope that have been launched in the past and in the future. So this is a Kepler mission, and that's the one that we've discovered all the exoplanets. But by now, Kepler's mission is pretty much over. And the next satellite up is TESS. And this is the next space telescope, and its job is to look for exoplanets, but this time concentrating on the stars that are nearby. Why? Because if they're nearby, they're easy to study. Okay. So that is TESS's job. So TESS will find a bunch of exoplanets, hopefully nearby, and the best ones will be chosen to be observed by the next space telescope, the James Webb Telescope. And this telescope job is to take spectra of the exoplanets, hopefully in search of signs of life. So, and after that, there are other telescopes. This is basically the tagline of the several space telescopes that have been launched in the past and in the future. So right now, this one is doing all the work, and eventually this one will take over. All these space telescopes are looking at exoplanets very far away, much further away from our solar system, and that's because they're all far away. But maybe the situation is going to change. So hopefully after I give this talk, maybe I will convince you that maybe there are now opportunities to study a body of another solar system nearby in our own solar system. Okay, so that's the purpose of this talk. This possibility of studying an extraterrestrial body in our own solar system was made possible by these two telescopes. These telescopes are called a 10-star telescope, and what they are is they are survey telescopes. A survey telescope is just a telescope that looks over a big area of the sky, as much of the area of the sky as possible, to look for anything you want. It could be looking for comets, could be looking for asteroids, could be looking for exoplanets, supernova, anything. But the main idea about survey telescopes is they cover. Okay. Yeah. Thanks. So the main job of a survey telescope is to cover a large area of the sky to find as many things as possible. Does that work? Okay. Like that? All right. So to be a good survey telescope, you need two things. You should have a large mirror, a big mirror, because the bigger the mirror, the fainter you'll be able to see. And hopefully have a big field of view so that you can cover a lot area, a big area.
Maybe better to use a handheld.
Yeah,
will you change that? Just a little bit. 刚刚他有讲到说，你虽然要去找系外行星都是很远的，可是呢，现在有可能在我们自己太阳系里面去研究来自别的恒星系统的东西，这是今天的主轴了啊。他说要研究这个东西的话，第一个你要有很大的望远镜，看到暗的东西；第二个要很宽广的视野。Pan-STAR 叫做泛星计划，台湾中央大学有参与泛星计划。
So these two telescopes, the Pan-STAR telescope, they're not very big. They're only 1.8 meter in diameter. But what they have that other telescopes don't have is they have a very big field of view. So the Pan-STARs, with only a 1.8 meter mirror, the field of view is 3.2 degrees. Okay. If you compare that with the other telescope, like the Subaru telescope, also in Hawaii, it's 8.3 meters. It's quite big, but the field of view is only half a degree. This one is the Canada-France-Hawaii telescope, CFHT for short. It has a 4-meter mirror, but again, the field of view is only about 0.6 degrees. So the field of view here for a survey telescope, the field of view is the name of the game, is the main thing. And Pan-STARs with a much bigger field of view than basically all the other telescopes, that's what makes it better than it just makes it excel as a survey telescope. So besides so it has a very big field of view, and on top of that, it has a camera that can take advantage of this field of view. This is the world's biggest CCD camera. A CCD camera is like the camera in your cell phone, but it's a bit better, but it's basically the same. It's a digital camera. So this is a Pan-STAR gigapixel camera. It has 1.4 gigapixel, much more than you have in your phone. And it has a huge, basically it's an array, a huge array of digital camera. So this is a camera for Pan-STAR to take advantage of this large field of view. So this is what makes it such a good survey telescope. So in October of last year, Pan-STARRS found a very unusual fast-moving object. And here is a discovery image. You can barely see. So it's this little faint thing inside the red square. So you can see it was very, very faint. And that's because it was moving very fast. And at the time, when the telescope people found it, and they said, okay, well, maybe it's just another near-Earth asteroid because it's moving so fast. So they observed it, and then they tried to compute its orbit. But that computer code just kept breaking. Every time they put in the measurements, the code broke. And they didn't know what was going on. So they got another telescope, this one, the CFHD telescope, to help out. So this one took some follow-up observations 3 nights after. And here is the follow-up observation made by this telescope. This is a 4-meter telescope, so it could see much fainter. And here's the image that it took. So you can see the object much better here than in here, just because it has a bigger mirror. So by this point, after these observations, they now have enough data to try running their computer code again, and this time it worked. And they found out why their code kept breaking. It's because this object turned out to have a hyperbolic orbit. What does that mean? I'll explain to you what a hyperbolic orbit is. But since it's on a hyperbolic orbit, it means that it came from another solar system. So.
OK， 这个其实蛮重要的。大家看到底下，他说现在就发现了一个特别有趣的天体啊，去年的10月18号发现的。底下的 A、B 2个 frame， 左边的那个是发现的那个图像，红圈圈圈起来的是那个移动的非常快的天体。大家注意到啊，在那个天体上面，这个影像上面，它是定焦在背景行星上面，所以那个天体跑得很快，但是很暗。他们一开始还以为这普通的小行星吧，那没有想到，你用上面那个4米的 CFHD 望远镜3.8米去看了右边那个 B 号，你有没有注意到，它就锁定在那个天体上面长期曝光，所以它是个圆点，两个是不一样的哈。你锁定在那个天体上面，其他的行星就变成拉线，那这两个差很多。所以看到那个以后，发现它是一个双曲线的轨道，双曲线的轨道跟椭圆跟圆形不一样，所以待会儿就听他讲为什么双曲线的轨道，告诉你是它来自别的太阳系。
Okay, now I'll tell you a bit more about orbits. If you guys took physics, maybe you learned Kepler's law. And Kepler's first law tells you that if you have an orbit around a star, like the sun, the shape of an orbit can only be one of 4 things. It could be a circle, like this. It could be an ellipse, like this. And if it's a circle or an ellipse, we call that, these are bound orbits. That means they're closed. So the star would be, like the sun would be over here. And if the orbit is a circle or an ellipse, it would just repeat itself over and over and over and over. So these are closed orbits, and they're bound. They're closed, they continue like this forever. On the other hand, the other 2 possibilities is, it could be a parabola or hyperbola. Parabola would look like this. Parabola and hyperbola would look like this. And you can see the parabola and the hyperbola are not closed. They're open orbits. That means they're not bound to the sun. So if something is on a parabolic orbit, it will sweep by the sun and it just keeps going. Same thing with hyperbola. It will make a close approach to the sun and it just keeps going. So the parabola and the hyperbola are open orbits. They're not bound to the sun. Okay? So the fact that this object that was just discovered is on a hyperbolic orbit like this means that it's not bound to the sun. That's why so it must have come from another planetary system. This might explain to you the difference between the orbits a bit better. Let's say you have a spaceship. You just launched a spaceship. Which orbit is it going to have? Well, that depends on how fast the launch velocity is. So let's say you launch a spaceship, right? Here it goes. If your launch velocity, the launch velocity is less than the escape velocity, then it's going to have the shape of an ellipse or a circle. But if you launch a spaceship with just enough velocity to escape, then it will have a parabolic orbit. It will look like that. Okay. But on the last possibility is if you launch the spaceship with much higher velocity than the escape velocity, then it will go on a hyperbolic orbit. Okay, so this explains to you what's the difference between all the possible orbits. Okay, it all has to do with how fast these things were launched.
我想大家都熟悉吧，基本物理，如果你那个速度小的话，旁速小，它就会进入一个圆形或者椭圆形的轨道，那个叫做速浮态，它就绕着这个天体转了。那如果你速度够大，刚刚好脱离的话，脱离速度，它就是一个抛物线轨道。那如果更大的速度的话，就是一个双曲线轨道了。所以抛物线和双曲线呢，这个天体都不会再回来的，它就是绕圈就出去了。
So, the object that was found by the Pan-SOL telescope was now given the name Oumuamua, and is now acknowledged to be the first object that came from another solar system that happened to be going by. So its trajectory is shown here. So you can see it comes in like this, swings around the sun, turn around, and went back out. You can see this hyperbolic orbit is very different from the orbits of the planets, right? The planets are here. They are near circular orbit. It's also very different from the orbit of a typical comet, this guy here. So you see, like this is a elliptical orbit, is bound to the sun, and these are the orbits of the planets, and then nearly circular, also bound to the sun. But this one, the path of Oumuamua, is a hyperbola. Comes in, swings on the sun, then it goes back out to interstellar space. It just came by for a quick visit. After a quick visit, it went back out.
How do you pronounce that? Is that a Hawaiian god?
It is Oumuamua is a Hawaiian name. I think it's supposed to mean a scout or some kind of a scout, an explorer. It's a Hawaiian name.
OK， 他说那个名字啊叫欧穆阿穆啊，大家不要把那个欧穆阿玛，欧穆阿玛就变台语了啊。欧穆， if you pronounce it 欧穆阿玛， it becomes Taiwanese. Yeah， 欧穆阿穆啊，它是夏威夷话，意思是斥候兵或者是哨兵的意思啊。那你看它的轨道下来，就是一个很典型的双曲线轨道，绕过太阳以后，因为太阳重力场的关系，一转弯就出去了。所以这是第一个发现从别的行星系统来的外面来的访客。
Okay. So here's another picture of its trajectory. So with the dates indicated. So back here, so it came in at this again, coming from above the plane of the ecliptic, swing around the sun, and came back out. So it was found around here on the 17th of October. And by the time it was found, it was already on its way out of the solar system. It didn't stay very long, right? It just came in very, very fast, swing on the sun, and went back out. And by the time we discovered it, it was already on its way back into interstellar space. The unusual thing about it is that it came very close to the sun. This is the orbit of Mercury. It came well inside the orbit of Mercury, so right here. So at this point, when it was closer to the sun, we call that perihelion. At perihelion, it was moving at the phenomenal speed of 88 kilometers per second. This is much, much faster than any spacecraft that we have ever built. Okay? So another evidence that it must have come from another solar system, because there's nothing in a solar system that can be moving with this speed. So it went swim on the sun and went back out. So once this interstellar origin was confirmed, everybody expected it to be a comet. Why did they expect that? Well, I'll explain. Besides the planet, our solar system contains a lot of small bodies. They're called asteroids and comets. Okay? And here are their pictures. The difference between an asteroid and comet is this. If you look at the picture of the asteroid, they look like rocks. And that's what they basically are. They're just chunks of rock. So they don't do anything. They're just rocks. In contrast, a comet, as you can see the picture, have this big coma. This thing, this cloud of dust and gas, that's called the coma. And in the middle, maybe you might be able to see the nucleus, but sometimes the nucleus is so faint we can't see it. But you recognize a comet by this big cloud of dust and gas, which is called the coma. The coma is there because comets are full of ice. So they go around the sun, but when a comet approaches the sun, it's heated up by sunlight. And when it's heated up, what happens to ice? When it's heated up, it evaporates. So the ice in the comet evaporate. The gas molecules escape into space, and as they escape into space, they take along dust particles. So that's why the coma is filled with dust and gas particles. And that's the difference between a comet and an asteroid.
Okay, Jane. 大家看到刚刚他的前面那张图啊，就跟大家讲这个欧姆阿诺啊，用非常快的速度扫过太阳，那速度是每秒钟88公里。看到那样的速度，你就知道它绝对不是太阳系里面的天体，因为这速度实在是超过任何一个我们在太阳系里面人造或者天然的那个物体啊。但是发现的时候，它其实已经经过太阳旁边了。那你把它的轨道回推，才会做出那样的一个高级别吧，一个非常精彩的轨道。那当时人们就想，可能是卫星，为什么？因为左边是小行星，小行星是石块，不会喷气的。彗星呢，多半是冰块跟灰尘组成的。那经过了太阳热的时候喷发出来的气体呢，就组成了彗发 ，coma 叫做彗发，跟凤梨长长的尾巴，所以他们一开始以为是会喷气的彗星。
Okay. So, all right, so the solar system contains a lot of comets and asteroids, and I'll show you where they live. The asteroids, most of them live here in the asteroid belt between Mars and Jupiter here. The comets have two reservoirs. They come from two places. One reservoir is called the Kuiper belt, and it's this guy that's located just beyond the orbit of Neptune. And then the other reservoir of comets is the Oort cloud, and it's a huge cloud of comets, very, very far away. That the solar system, the planets are way down here. The Oort cloud is enormous. Basically, it goes out to the edge of the solar system, and that's another. So this is another reservoir of comets. So the asteroid belt contains the asteroids. Short period comets live in the Kuiper belt, and the long period comets live in the Oort cloud. So over the age of the solar system, all these three reservoirs have kicked out a lot of bodies. We have kicked out a lot of asteroids and a lot of comets. And the question you might ask is, well, how did these unlucky comets and asteroids escape from the solar system? Well, it usually has to do with scattering. Like in this picture. This picture shows you the orbit of Jupiter right here, and here's the orbit of Neptune. And this red guy, it just happened to be an asteroid or comet. So it comes in, maybe, and it was unlucky enough to come close to Neptune, which scattered it, so it changed the orbit and then kicked it out of the solar system. So this is a typical picture of showing you how a typical scattering event takes place. And this is how the planets got rid of a lot of asteroids and comets. And what brings these unlucky asteroids and comets near a planet in the first place? Usually it happens to if the asteroid or comet is involved in something called the resonance frequency. Okay.
所以大家刚看到是说有别的天体跑到我们太阳系来，那Jane现在讲的就是说我们自己的太阳系里面有3处小天体聚集的地方，那也会大行星也会把这些小天体甩出去。他说这个红线呢，就是个运气不好的彗星或者小行星，先经过了底下的海王星，那海王星它转个方向以后，运气不好又经过了更大的木星，那转2个方向以后呢，它的方向就会朝太阳系外面走了。所以我们的大行星也不断的会把太阳系里面小天体给甩出去。
Okay, now I'll tell you what is a resonance frequency. Probably the best way to explain that is just to give you an example. So an example of a resonant frequency, pushing somebody on a swing. I'm sure all of you have played on a swing, or you have pushed somebody on a swing. If you push the swing at the right frequency, at the resonant frequency, you find that the swing, the amplitude of the swing gets bigger and bigger and bigger. So if you push at the right time, this kid on the swing could theoretically go all the way around. Okay? So the point here is, if you push the swing at the right time, it can go very high, very easily. If you push at the wrong time, the swing can actually stop. Okay, so the point here is if you exert a force at the right frequency, which we call the resonant frequency, and every system in the solar system or mechanical system, everything has a resonant frequency. We just have to find out what it is. So if you push a kid on the swing at the right frequency, the resonant frequency, the swing can go very, very high. Okay, that's one example. Another example, well, how can you break a bridge? By shaking it at the right time. Same thing. Basically, you exert a force at the right frequency. I'll show you. So these are 3 people. They don't weigh that much, all 3 of them. They're not that fat. But just by shaking the bridge at the right frequency, you can see the amplitude of that bridge. The whole bridge is just bending like a rope. and it just comes from the fact that it's not that these people are extra strong or anything. It's just they're shaking it at the right frequency, at the right resonance frequency of the bridge. So the point is exert a force at the right time, over and over and over again.
Were they doing something crazy, or this bridge was built for shaking?
This was done by some physics department, so they would send out to go shake a bridge.
所以这物理系的老师跟学生干这种事情，这个共振频率。感觉后面很像何梦初老师。
All right, so those are two examples. This is all the example of a swing, resonant frequency, shaking a bridge, resonant frequency. Or what about else? How about in the solar system? We're not in space. We're not talking about bridges and swings anymore. But everything in the universe orbits around something, and so that's why the frequency come into play. Okay, I gotta start this thing again. Okay, all right, let's start from the beginning. So this just shows, it's an example, there's a star. You say the star is here, and it just happened to have two planets, and with the red and the blue planet, and the red and the blue planets are located just at the right location, so that the red planet will make two orbits every time the blue planet makes one orbit. Okay? So there is an example of a frequency. So the blue period divided by the red period is 2 to 1. Okay? And then, so we call that a mean motion resonance. So I'm going to make this movie run, and you're going to see what's going to happen to this whole system. Every so often, all three bodies will line up, like here. So they line up again. So they just keep going around, and every so often, all three bodies line up along this line. And this line slowly also precesses. The fact that this line just slowly rotates comes from the fact that it's these two bodies. They repeat their geometry over and over and over again. Okay? So they have a special relationship with each other. And we call this a mean motion resonance. All it means is that the period between one body and the period of another body forms a nice integer.
OK， 大家现在看到的是共振了。刚才举了2个例子啊，一个是荡秋千，你推一个秋千上的人；另外是去傻去极端无聊的去摇那个桥啊。那第3个就是这个行星的共振了。大家有注意到红点绕2圈，刚好蓝点绕1圈，所以它每一段时间就会有跟那个太阳3个排成一直线的时候，那每次经过这样一直线的那个蓝的就会对红的产生作用力，所以这就是一种共振的旋转。
So the point here is that every so often, all these three bodies line up perfectly. And it happens every time. This guy go around 2 times, every time this guy go around 1 time. And so this geometry, when they all lined up, repeats over and over and over and over and over again. So every time they repeat, there's this gravitational kick that is applied to these bodies. And it's like getting a little kick over and over again, just like a swing. On a swing, you get a push over and over and over again at the right time. And over time, over billions of years, these little kicks add up. And so asteroids and comets that tend to be in this kind of special geometric configuration, they tend to develop extreme orbits. And these extreme orbits bring them close to the planet, and then they get scattered out. Okay? So this is an example of resonant frequency in the solar system. So over time, we know that the asteroid belt has lost 1 Earth mass, has picked up about 1 Earth mass worth of asteroids. The Kuiper belt has ejected about 10 to 100 Earth masses of comets, all thanks to resonant frequencies. And the Oort cloud has kicked out maybe 1 to 100 Earth mass. This number is very uncertain, as you can see, but that's because we don't know much about the Oort cloud. So you add all of this together, and you see that the number of comets ejected outnumber the number of asteroids ejected by at least a factor of 10 to 1. So we think, well, if the other planetary systems are like ours, then maybe they also ejected many more comets than the ejected asteroid. So that's why we expected any interstellar object that we find would be a comet.
我觉得这个其实很精彩，因为刚刚大家会看到共振的关系啊，所以呢就会让其中一部分天体的轨道越来越极端。 越来越极端的结果呢，它就会有很大的机会被甩出去了。那科学家的研究发觉，过去很长时间以来呢，我们自己的小行星带，火星跟木星之间小行星带呢，已经因为这样共振甩出去了一个地球质量的总物质，很多小天体但加在一起是一个地球质量。那没有想到古柏带海王星以外的古柏带已经甩出去10个到100个地球质量的总物质了。那欧特云最外面的欧特云呢，损失掉1到100个地球质量，但是呢，古柏带跟欧特云都是彗星。所以你如果想到说别人的行星恒星旁边也是跟我们情况一样甩出来的话是10比1，就甩出来的彗星跟小行星相比10比1的话，那你会期待多半在星际空间里跑来跑去的应该是甩出来的彗星比较多。
So when the Hawaii people announced that they found the first interstellar object, of course every telescope on Earth turned to try to look at it, and this is a list of all the telescopes that try to study the object. Hubble Space Telescope is here. They also took a look. Spitzer, the Magellan Telescope, basically all the world's biggest telescopes were here. We're down here, they've Jewitt and I. We have the smaller telescope of all of them. We have access only to a 2 meter, and everybody else has the big telescope. And so this just shows you what night we observed, and we observed on this night and this night. Okay. This just shows you that basically every astronomer that had access to a telescope was looking at this object.
Jane, I think this is fun.
Okay.
就是知道这个天体宣布已经发夏威夷说找到这个天体以后呢，好多天文学家都排在那个队，然后用望远镜去看它。他圈出来的是他跟他的老板跟他的那个老师Jewitt 共同观测。你不要看到 NOT 是 NOT 是没有望远镜，不是NOT 是它的 Nordic Optical， 就是北欧的 Nordic Optical Telescope， 北欧的光学望远镜，实际上是在非洲北部外海加大利群岛上面，这3个我待过的加大利群岛上面的那个望远镜，2.5米，就是所有的望远镜里面，因为它们是比较小的，别人都是8米、10米的，他们比较小的望远镜。
So these are the 2 telescopes we have access to. This is the 2.5 meter Nordic Optical Telescope on La Palma. It's an island in the Atlantic, belongs to Spain. Here it is. And the other telescope we have access to is this telescope called the WIN telescope. It's 3.5 meter at Kipik, Arizona. And this telescope is 2.5 meter. By today's standard, this is considered very small, but it was a fantastic telescope, and we got wonderful images that I'll show you in a second. So the point here is, it's nice to have the Keck telescope, the 10-meter Keck telescope, but not everybody has access to that, and you can still do really, really nice work with a small telescope if you know what you're doing. So we use observations from here, and these are the measurements that we made, and I'll talk about that next. So this is pictures that we took of the object. Everybody was looking at this object, and everybody wanted to find a coma, right? We expected this thing to be a comet, so where is the coma? Well, so we took lots of pictures, and this is 12 images added together. Why did we take so many pictures? Why, you might ask, why did we take a long exposure? Well, we couldn't because the object was moving so fast. So here's the object right here. The telescope was tracking the object, right? So the object was moving, and the telescope was following it. So it looks just like a point source. And these trails, these are stars, right? We were following this thing, so all the stars were trailed. Okay? So this is a sum of 12 images added together, and you can see there's no coma, right? We looked very hard, but there was no evidence of a coma. And this is just the same image as this one. We just took out all the star trails. So here it is, and it's clear. There is no coma.
OK， 那他们现在就开始观测，他们虽然用的望远镜是2个，一个是2.5米的，另外就是3.5米的望远镜，比较小的。可是呢，他把12张照片叠在一起，上面那一半你会看到，中间的是因为它移动很快，所以你不希望做长曝光，那所以它锁定在那一个天体上面的，其他星星就拉出星轨来了。那下面这个就把星轨移掉，就光剩这个天体了。重点是，如果你真的相信它是来自别的恒星旁边的彗星的话，为什么没有彗发？他们很努力找不到彗发。
Okay, so we looked for a coma. We did not see a coma, so we thought, okay, it's not a comet, it's an asteroid. But that's not the end of the story. We were able to calculate how big it was based on its brightness. If you measure the brightness of something, well, that brightness depends on how big it is, the size, depends on how far away it is, the distance, and how reflective it is. So we were able to measure the brightness, right? We measured this one, we measured this one, the distance. We assume this is 10%. reflectivity. Because why 10%? Because most asteroids in the solar system have 10% reflectivity. So, you plug these numbers in and you can calculate the diameter. And we found that the diameter is about 120 meters. But this number is very misleading, and you will see why. Okay, I want to talk about a spinning egg. Let's say you have an ellipsoid with 3 axes. We call that a triaxial ellipsoid, like an egg, right? An ellipsoid body with 3 axes. Let's say you have this egg, and it's spinning in front of your eyes. And you want to measure its brightness. If you measure the brightness of a spinning egg, it will look something like this, right? And the brightness will go up and down, right? So when the fat side of the egg faces you, it will look bright. When the dim side faces you, the pointy side, it will look dim. And the fat side faces you again, it will be bright. So if you measure the brightness of a spinning egg and you plot it, it will look like this, right? Okay, so all I'm just trying to say is if you assume the object is like an ellipsoid and it rotates, the brightness variations will go up and down, up and down. There will be 2 maxima and 2 minima in one rotation period.
如果要知道它的大小本质的话，你要知道它的亮度，你只能看到的是亮度，但它亮度是跟它的大小、距离还有它的反射率相关的。那反射率就假设它是 10%， 因为每个小行星几乎都是在 10% 左右。但是他们现在发觉了，它如果它的亮度变化的很离谱、很极端的，所以它想是一个3轴的椭球体，就像个鸡蛋这个样子。
So remember this picture? Brightness variation of an egg. Look, it looks just like the brightness variation of this interstellar object that we measured. So this is the brightness variation measured over 3 different nights, right? Different colors, 3 different colors, 3 different nights. And we put them all together, and it looks just like, you have a spinning egg in front of you. And so again, brightness this way, and this is time. So one rotation period is about 8.3 hours. Alright, so we measure that. Alright, so it rotates at 8.3 hours every spin period. But the unusual thing about it is how bright it becomes compared to how dim it becomes. This is a very steep rise, going from very dim to very bright, falling back down and up again. Okay? So this tells you how steep, how much the brightness variation from maximum to minimum is such a big number. It tells us that this thing has a very unusual shape. And it tells us that this maximum is at least 6 times brighter than this minimum. And this ratio, so that tells you that the long side divided by the short side is at least 6:1. It tells you the axis ratio. Okay, so that's if something is 6 times longer than the short side, that means that has a very elongated body.
Yeah, 就是你看那个亮度，它最亮可以到21.5等，那最暗可以到24等。2个差到6倍，所以他们认为说它应该是个长的东西，狭长的东西，长边跟短边的比是6:1。
So that was our measurement, and this is measurement from other people who were always also looking at it, all the big telescopes, and they found something similar. But the strange thing is that nobody could agree on the same number. So these people found that the spin period is 7 to 8 hours. We found 8.3 hours. And they also found the axis ratio, the long side divided by the short side. They found a factor of 10:1. We found 6:1. So there were basically every telescope was looking at this object, and nobody could agree on the same numbers. So we had to come to the conclusion that because the brightness variation don't agree, that this thing maybe is doing something. It's spinning, but it's spinning in a very funny way. It's spinning around more than one axis. So that might, to call it, is tumbling.
Yeah, 那这个天体应该在翻滚，它的翻滚呢不是环绕着1个轴做很规律的翻滚，而是环绕2个轴做翻滚的。所以每个团队所观测出来的那个亮度比跟长短边比都是有点差别的，数字都不太对劲，都不一样。
Okay, just to summarize what we learned about the object. With an axis ratio of 6:1, it looks something like this, kind of like maybe like a cigar or something. The long axis is maybe like 400 meters roughly. So it's about 400 meters long. It has a very elongated shape with an axis ratio at least 6:1, maybe even more. And that's the most unusual thing. I should point out that nothing in the solar system has this kind of axis ratio. I think the biggest number that we know of is 3:1 in asteroids. So this axis ratio is unheard of in the solar system. We expect it to be a comet, but there was no coma, and it spins at the rate of about 8 hours.
OK， 他说你用亮度变化去算出来的话，它至少长度是400米左右，但是呢，长边跟短边比是6:1，这从来在太阳系里面没有看到过。太阳系里面的小行星最多是3:1，然后它又没有coma，没有会法，然后它的翻滚的周期是8小时左右。这是艺术家画的，请我记得，这上面写 artist concept。
Right. Oh yeah. Sorry. This is an artist concept. This is not the picture that we took.
那不是照片，那是艺术家画的。
Okay. All right. So we think. All right. So, but still, it's not the end of the story. This thing was last observed in January of this year by the Hubble Space Telescope. By that time, it was very faint. No telescope on the ground could have seen it. So, but the Hubble Space Telescope observed it. And so by that time, so that makes like 4 months of observations. The astronomers put all the observations together, tried to fit an orbit, and they found something very unusual. They found that its orbit could not be explained by gravity alone. So there was something else going on. And here's the evidence. So this shows you the path of the object, Oumuamua. So the sun is here. It comes in like this, turn around, and it goes on. But if you zoom in to this section right here, you see something like this. This green line is where it should be if there was only gravity affecting it. But this blue line is where it was measured. So you can see it traveled 100,000 kilometers further than it should have. So this is evidence that something else is acting on it. There's some other acceleration other than gravity.
OK， 他说这个东西很奇怪的是，如果单纯是跟太阳的重力相互作用的话，它最后那一段路呢，应该走那个绿色的，只有重力作用在上面，它应该走到那段路。但是呢，竟然超过了10万公里，所以它除了重力之外，它有别的力量作用在上面，大家会觉得越来越有趣了。
So, all right, so it has non-gravitational acceleration. What could it be due to? Well, the simplest explanation is that maybe it's a comet. It's outgassing, right? It's spitting out gas and dust. And I'll talk about outgassing next. So, what's outgassing? Well, it's just spitting out gas and dust. And what's the result of outgassing? Well, that's exactly what a rocket does, right? It outgasses. It spits out gas, and that's how it moves forward. Because that's what Newton's third law says: every action has an equal and opposite reaction. So if you shoot out stuff in one direction, you're going to move in the other direction. Okay? So if you're outgassing, then you expect the rocket effect.
就是喷气，喷气出来的话，它就会第三定律，作用力等于反作用力。所以 outgassing 其实就是喷气的意思。
So if this thing is outgassing, as it seems to be, because this has non-gravitational acceleration, well, then what is this thing? Is it a comet, right? Comets outgas, they eject gas and dust, so they also experience a rocket effect. So right here, so this is a picture that I showed you earlier. This comet the level outgassing is really high, right? It's a huge comet, so it must be accelerating it has a strong non-gravitational acceleration. This one is not outgassing so much, this one just has a little bit. But in any case, outgassing means that it has to accelerate. It has to, the rocket effect has to exist. So, if Oumuamua is a comet, where is the comet? We didn't see it. Even the Hubble Space Telescope did not see it. So if there's some mechanism that we don't know about that allows a comet to spit out gas and dust, and that's not detectable, I don't know.
Yeah， 那如果说是彗星的喷气的话，像左边很强烈的喷气会看到漂亮的彗发跟长长的彗尾啊。那如果是比较弱的喷气的话，在右边这边你也会看得到小小的喷流出来。但是如果它是个彗星的话，为什么看不到彗发？连哈勃望远镜都看不到，那它整个的就不存在了。
So the simplest explanation is this thing is a comet, it's spitting out gas and dust. But the problem is we didn't see a comet. That is a problem. So some people say, well, maybe it's not a comet. Well, it kind of looks like a rocket. So could it be a rocket body that is spitting out gas? Maybe. Or could it be a spacecraft with a little iron thruster? This is actually the Dawn spacecraft. This was a mission that went to observe some asteroid. And it looked just like this. The shape is kind of similar, with a very long shape because of the solar panels. And it has an iron thruster spitting out gas in the back. So this thing is accelerating. Right? What is it due to? Is it a comet? In which case, where's the coma? Is it a rocket body? We wouldn't see any. We wouldn't be able to see the gas that is spit out. Or is it a spacecraft? Again, we wouldn't be able to see the gas that's spit out. So, is it a comet, rocket body, or a spacecraft? We don't know.
Yeah. 所以它到底是什么？是不是彗星？可是看不到彗发。那是不是一个火箭？火箭的话会往后面喷东西啊。但另外是曙光号，曙光号刚去过了造神星跟谷神星两个小行星，然后任务现在刚结束了啊。但是它背后有喷出一个小小的离子引擎来，但长长一条一个形状，所以这是几种可能的形状，跟自己也会喷气的东西。
And there's one final thing that it could be. Well, it could be something like this. This is a solar sail. This is an Icarus solar sail, 14-meter dimension, was built by the Japan Space Agency, and it was built to demonstrate that momentum from sunlight can push a sail, just like a sailboat. Right? The sail on a sailboat is pushed along by the wind. You can build a solar sail where the sail will be pushed along by sunlight. Sunlight is very light, right? You go out in the sun, you don't feel sunlight hitting your skin or anything, so it doesn't have any mass, but it has momentum. So if all these photons hit a sail, all these little bits, all these little momentum from every photon add up, and it can push along a sail, just like the wind, the way the wind can push along a sail. So maybe it could be could be a solar sail, and some people will say that maybe it's a solar sail that came from an alien.
说可能是太阳帆，是外星人做的太阳帆啊。这是2010年日本人做的一个14米的太阳帆，叫伊卡鲁斯。伊卡鲁斯是神话里面的一个人物啊。太阳帆，那太阳帆呢？太阳光打上去，太阳光的光子是没有质量，但是有动量，所以那个动量可以推动这个太阳帆往前进，就是加速这个卫星的。所以是不是外星人的太阳帆？
This would explain why it would be pushed along by sunlight in addition to gravity. And this could explain the non-gravitational acceleration. Okay, so lots of people are thinking, well, this is an alien spacecraft. And so some people try to answer this question. And so that these people called the Breakthrough Listen Project, and their job is basically to search for extraterrestrial communication in the universe. So they took this telescope, the Green Bank radio telescope, 100-meter aperture. They pointed it at the object and they tried to look for radio broadcast. They didn't find any, and they searched from 1 to 12 gigahertz, but they did not find any communication.
他们大家想说是不是外星人的太空船啊？所以赶快找无线电波望远镜去听听看它有没有任何无线电波讯号。但在1到12 gigahertz 里面没有听到任何声音。
Okay, so what's next? Well, this thing is gone. It came by and it's gone. It could be a spacecraft, as some people claim, but the point is we'll never know because it's long gone. But what gives us hope is that if we found this one, we'll find more, and this is the reason. So it was found by the Hawaii telescope, and it has been working by 2 or 3 years. So the discovery rate is like half an object per year. So this tells you if this is the discovery rate, that means there are lots and lots of these things. And there should be like 6,000 of these objects from here to the distance of Pluto. If there's so many objects like this, you can be sure that another one will pass through. And next time, we hope that this telescope, the astronomers believe that this telescope will find most of them. This is the Large Synoptic Survey Telescope. It's being built in Chile. It's 8.4 meter. It will start working in 2022. Anyway, it will cover the whole sky every 3 nights. So we expect that this thing will discover on the order of about 1 interstellar object per year.
Yeah. 大家现在看到的就是说，如果它的望远镜运作了2年就找到了1个，所以呢，每1年应该找到0.5个。那这样算起来的话，从太阳到冥王星中间应该有6000个这些从别的恒星旁边来的星际天体了。如果真的有这么多的话，他们现在在做个望远镜，镜子很大，8.4米的望远镜啊。 2022年会开始运作了，那就是一个大的巡天观测望远镜呢，应该每年能发现1个，10年的，它每大概3天就把全天扫过一遍，非常巨大的视野，3度的视野啊，去扫全天，所以他们希望很努力的找到更多的星际物质、星际物体。
So the fact that an interstellar object came so close to the sun, it came close to the Earth orbit, this raises the possibility that maybe we can send a space mission to meet the next one. The largest challenge in intercepting an interstellar object is how fast it's moving. It's moving really, really fast because of hyperbolic orbit. So the cruising velocity of this object, or more, its cruising velocity is 26 kilometers per second. This is faster than any spacecraft ever built. So it's going to be difficult, but the point is, But since it comes so close to the Earth and the Sun, it is possible that we can send a mission to meet it. And the way to do it is if we discover it early. If we discover something like this early on, we could have sent a spacecraft to intercept the object. It's not going to be easy, but there's a good reason why we should try to do it. And the reason is, this kind of mission is the only way to study an object from another planetary system close up. Right? We have no technology to go to the nearest star. There is no spacecraft that can take us to the nearest star. So having one come to us is the best. It's the only way to study another extraterrestrial body close up.
所以你会觉得天文学家真的很疯狂，他们现在想的是要拦截这些来自外星的天体啊，因为你自己只有在太阳系里面，那来自外星的天体呢，偶尔经过了你自己的话，你能够太空船出去，问题就是它的速度太快，正常的航行速度是每秒钟26公里，但如果你发现的早的话，你的确是可以拦截它的，因为你就可以很方便的去研究别的恒星旁边行星系统是什么样子。
Okay, so how might we do this intercepting mission? Well, let's take this object as an example. So this plot just shows you the orbit of, here's the purple, here's the Earth, the Sun is right here, and this red trajectory is the Oumuamua coming by. So this is its path. So you can see it crosses the Earth's orbit twice. The first time was when it's coming in, turn around the Sun, then it crosses the Earth's orbit on the way out. So if we had discovered this thing early, we could have had a spacecraft and we could have launched it at the right time so to meet the object on its way out the second time. See? And you can see it wouldn't be so hard because basically you don't have to go very far because it crosses the Earth's orbit. So the point is, if you're ready, if you had discovered this thing early and you were ready for it, it wouldn't have been very difficult. I mean, it'd be something to do, but the point is you don't have to go very fast because it crosses the Earth's orbit. So the point here is early detection is essential if you want to intercept something like this.
所以提早侦测到很重要，因为它其实经过了地球轨道2次，7月份一次，然后10月份一次，所以7月份你就知道已经看见它的话，你如果有现成太空船，你就发射，7月20号发射以后，10月26号当它第2次经过地球轨道的时候，就可以拦截那个天体了。
Okay, I'll have to hurry because my time is coming to an end. So the next one, all right. So I point out that if we found this thing early, maybe we could have done something to intercept it. But the next question you have to answer is, how do you get something moving about 30 kilometers a second? Right? This is no spacecraft ever built has ever reached this kind of velocity. How do you do that? So you can't just launch a spacecraft and reach 30 kilometers a second. The only way to do it is if you have some sort of gravity assist. Okay? So if you have rocket thrusters and gravity assist, you might be able to do it. And the way to do it is you make use of something called the Obert effect. This is an effect discovered by Mr. Obert. And what he discovered that if you have a spacecraft and you want to fire the rocket, you should fire at the right time. You should only fire your rocket when the spaceship is moving at the fastest. Why? Because that's how you get the most gain in the velocity. And this is an example. So in the solar system, right, everything is an elliptical orbit. If you launch a spacecraft, it goes around the sun. This is at perihelion. When it comes close to the sun, the spaceship will be moving much faster here than it's here. That's what Kepler's law, second law tells us. So we know that. All right, we say, okay, we know the spaceship is moving much faster when it's near the sun. So this is when we should turn on the rocket. And this is how we get the most velocity gain. And if you do it right, and how fast it can go, it just depends how close you can get to the sun. If you can get close enough to the sun, you can easily reach something like 100 kilometers a second. So this is how you reach 30 kilometers a second.
它有个效应，就是你在近日点的时候发射火箭，它的速度就增加的最快，说不定可以到每秒钟100公里。
And this kind of trajectory is already being done. The latest spacecraft launch is called the Parker Solar Probe. This is a spacecraft launched to study the sun and the solar wind. And this path is shown here. So it was launched in August this year. And the first thing it's going to do is cross the orbit of Venus. And every time it crosses the orbit of Venus, it changes the orbit. So it gets closer and closer around the sun. So it's going to do this loop, 7 times actually. And every time it crosses the orbit of Venus, the orbit will change a little bit and get closer and closer to the sun. So eventually, when at the closest point to the sun, it's going to reach a velocity of 192 kilometers per second. right? This is a phenomenal velocity. So this is the kind of velocity we need to intercept an interstellar object.
Yeah, 帕克望远镜是去研究太阳的啊，所以它就一直绕着太阳转。但每次经过金星轨道的时候，它就会重力加速，所以速度会越来越快，到最后超过每秒钟的192公里。
So you can do this one way, but this takes about, so this mission is going to take about 6-7 years to get close to the sun. If you don't have the time to wait, then you could do something different. Maybe you can use Jupiter to get yourself close to the sun. So for example, you could launch a spaceship from here on Earth, go by Jupiter, change the orbit, get close to the sun, and then reach the high velocity that way. Altogether, the summary of this is that if you use gravity assist from the sun, you can reach very high velocity at 30 to 7 kilometer cruising velocity.
Yeah， 就是你可以用另外方法把地球发射入太空船，经过木星旁边，绕回来再经过太阳旁边，2倍的这个2次的重力加速的速度很快。
Okay, so that basically my time is up. I'll just try to summarize. So last fall, the first known interstellar object called Oumuamua went through our solar system. It's not very big, it's about 400 meters long, but has a very funny, elongated shape. But the most peculiar thing about it is it has non-gravitational acceleration. We don't know why. It could be a comet, but if it's a comet, it's a very funny comet because we couldn't find any coma. But the thing about it is that, so we don't know what it is. So there's no chance to really find out what it is. But many more will be discovered. Right? So we're expecting more to come through our solar system. And if that is the case, then it's possible to send a space mission to meet the next interstellar object to find out what it's really like. And that's it.
掌握它，所以掌握得非常好。那我们会有一点点时间来问题啊。但是大家都知道讲的今天主题的内容是什么吗？就是终于发现的第一个应该是来自别的恒星旁边的天体，它可能在星际空间里面飘飘荡荡，竟然在去年高速穿越了我们的太阳系。穿越时间很短，7月份过来，10月份就走掉，短的时间就走掉。但是呢，第一个，它走的方式不是单纯靠重力，光这句话听了就会毛骨悚然。它走的方式不是单纯靠重力，你在天文在上面你就靠重力啊。但你除了重力之外，还有什么别的力量？就是 outgassing。如果那个彗星本身里面有气体或者是冰块，太阳一加热，它喷气了，会改变它的方向，增加它的速度 ，fine。但怎么找都找不到挥发，所以它没有喷气。那到底是不是外星人的第一节火箭？那记不记得地球上人们发射上去第一节火箭会掉下来吗？你万一外星人在发射太空船的第一节火箭随便扔了以后，它刚好掉到太阳系里面来。长那样就很像，细细长长的，搞不好你靠近看就看到商标啊，上面写的外星人做的啊什么的。So I'll just entertain a few questions.
Sure.
Yeah， 有没有问题要请问Jane 同学们
Who thinks it's an alien? Who thinks it's an alien?
认为是外星人请举手。Yeah， 充满了好奇。Yeah, usually we were educated not to believe anything about alien, but this one is really alien thing.
And you know, it was found with not in 2 or 3 years of survey telescope. So the statistics don't lie, or sometimes they do lie. But in this case, they don't lie. So we expect more to come through, right? One came to our solar system, more will come by because you know that's just law of statistics.
Yeah， 他说统计上面的定律就是说，你只要开始看到第一个，以后你会看到更多。为什么？因为这个望远镜开始做巡天了，1-2年的时间就找到了一个。那以后当大家投入的时候，更多的就会出现。
Maybe. Okay, so should we send a spacecraft to meet the next interstellar object? Should we or should we not?
要不要去
Yeah.
去送给太空船？
What if they turn out to be not friendly?
Yeah， 认为希望下一个 I ask you a question， 希望我们下一次再出现的话，赶快送太空船去看它是什么东西的，请举手。希望的。Oh, so they want to send a spacecraft over there.
Send a mission. Oh, okay.
Okay.
But it could be unfriendly aliens. That's the point.
但如果是不友善的外星人的话，刚举手那些人要负最大的责任。Those people who raise their hand have to be responsible if they are unfriendly. Yeah. OK， 有其他的问题吗？
Any other questions?
OK， 这边。
Sorry. I have three short questions.
Okay.
First one, is about the terminology. So do you mean that non-gravitational means the gravitation force not coming from the sun?
That's right.
Okay.
Right.
So the second one is the orbit is the hyperbolic, right?
That's right.
And I noticed there is a slide in the first slide. You mentioned that it's a hyperbolic orbit, so therefore it's not coming from the sun. So do you mean that you can see clearly that the focus is not the sun?
Well, the focus is at.
The focus of the hyperbolic is not the sun. So
the point when it's near the sun, it was pulled in by the sun. So it did feel it was sent out from another planetary system, and it just going along. Then it came near our solar system. It was pulled in by the sun, and then it continued out.
Okay, so it's pulled in by the sun.
Yes, but it was not captured. It just it was deflected. The trajectory was changed. Okay, so I was just going to show you a picture.
我想先跟大家翻译一下好了。刚刚问的问题是说，重力如果不是重力的话，它额外的力量去拉扯它。他说那个天体是被太阳拉扯进来的，因为太阳也是个巨大的重力场嘛。那天体刚好从这个方向过来，所以被太阳拉进来以后，一转弯出去了。可是会发觉那个天体经过我们太阳系的时候，除了太阳的重力之外，还有别的力量。
But it goes like it doesn't go in circle. It doesn't go around the sun, but it was deflected by the sun. So coming like this, deflected around the sun.
Here's a question: If you see object in our solar system,
yes.
Do you see hyperbolic
orbit? We do not see hyperbolic orbits in the solar system because everything in the solar system goes around the sun, either in an ellipse or circle.
If you're looking at one object who unluckily was scattered out,
yes.
Kicked out away.
On the way out? If you saw that, then it must have been scattered. On its own, it would not have done that.
也是正常的天体在太阳系里面不会有双曲线轨道的，除非你是被甩出去了。要先进来这个天体有双曲线轨道，你知道它绝对不是太阳系的东西。
And I have also a question about why do you think the first the Umama was observed just last year?
Yes.
What's special about last year? Why?
There was nothing special about last year. It just coincidence.
Why?
Oh, so your question is why did we not find others before that?
Right.
Because survey telescope. Right. You need what do you need? You need a good survey telescope. You need a big enough mirror, and you need a big field of view. We haven't had good survey telescopes until now. This is very recent. Right? So these things, only one of them is working. The other one's not working yet. And this one's only been working about 2-3 years. That's it.
对，关键就是说你没有很好的巡天望远镜。This is so sad because in 1995, 96, we had a collaboration with the United States and China. We were using a 60-centimeter Schmidt telescope to do a survey, but I guess it's too small. Schmidt, 60.
This thing was very faint. Look how faint it was, right? You can barely see this thing at all.
大家有没有注意到，你把屋里面光打开一个光害 light pollution you don't see it at all，
right.
你完全看不到这个天体了。就是因为巡天望远镜大的要够大，然后视野要够大，而这样真正好的巡天望远镜到了1.8米的，最近才出现。过去都是小的做巡天的，所以你只能找到比较亮的天体，像这个。
Right. So you need a good telescope. So 1.8 meter is not very big. The good thing, but this is in Hawaii. A 1.8 meter telescope anywhere else would be much worse, and it would not have found this thing at all. Right? It could barely find it. This picture was taken with this is a 4-meter telescope. So the point is, you need a big enough mirror and you need a big field of view to make a good survey telescope. And we didn't have anything like this.
That's Maui, right? Maui. 对，这是在夏威夷。夏威夷的话，大岛当然天气很好，但是在马尾岛上面，在大岛上面，天气也很好，非常高的地方。他说，同样的望远镜，如果不是摆在夏威夷的高山上面，你是摆在全世界其他地方的话，根本看不到这个天体，远观的条件没有很好。所以现在慢慢这些客观条件成熟了以后才形成，开始发现外星人的东西。还有其他的问题 ？OK。
this object looks like the alien stuff. So were those SETI people getting very excited about this?
Well, they did try to. They did look for radio broadcasts.
So how many dishes
they had
equal to this object at that time?
Only one. That one dish that I showed, right? And they listened and they didn't hear anything.
We need a bigger dish.
Maybe, maybe.
Maybe they were just whispering.
And which frequency?
Yeah, no, but so we need to get all the SETI people. There are plenty of SETI people around there.
I'm sure they tried, but they didn't hear anything. Okay, if there's a question from any student, it's only so far from only the professors.
其实我觉得刚刚我觉得老师说的很好啊。他说你 SETI， 他说 SETI 就是寻找外星人的组织嘛。那他用了大望远镜，不是看就是大望远镜啊，大的射电电波望远镜去听了，然后他选的是1到12 GHz，1到12 GHz， 你怎么知道外星人在这个波段里给你通讯？所以有很多问题。好，同学们有问题，学生们有问题。有问题没有关系啊，问中文对吧？翻译台语。好，那边。通常听到的外星人的故事，大家会觉得很本身的。2018年第一次接触到外星人，说好玩，2018。站起来吧，要不然看不到你。站起来。
那个他说是从别的星系甩过来，那应该是很不规则。那有没有可能会击中我们星系的那个星球之类的？
就打到我们太阳。
对啊。我要是干扰我们的运动。
Because it's randomly coming in, is it any possible for direct collision with our planet?
No, I think from the orbit, we would have known. By fitting an orbit, you would know if it was going to hit the Earth. Yeah, it could have, but the chance of it was very, very small. So.
几率很低的啊，你在从远远科学家也知道，远远起来你看这个点就知道它的轨道是什么。
May I get a number?
He wants to get a notebook. I said I'll give the notebook to the next question. He said,
之前听过一个理论是费米悖论啊，人类历史大概只有5000年啊，5000年就有这样规模，所以在银河系假如有其他的外星人的话，那其实有点不太合理吧？我觉得，对啊，有点不太合理啊，因为人类只有5000年就有这个规模，那假如有其他人，那只要差那个，只要再多了1-2千年，应该就可以在那个银河系里面发现了吧？所以就是我觉得。有外星人好像在银河系的话，有些外星人好像有点不太合理，就是跟费米悖论的说法这样。
Okay, Fermi's paradox that a human being evolved for like 5,000 years. We have current technology, but if we have other aliens out there that are like 1,000 years more advanced than us, then they should be able to travel around, and you don't see it.
Oh, so you're saying that if we get help from aliens, then we would...
We should be able to see aliens.
Oh, so is he saying that our technology was made possible by aliens? No.
We only, it took us about 5,000 years to evolve to such a technology.
Right.
But if aliens as civilization, like a couple more 1,000 years ahead of us, they should be able to fly around in the galaxy.
Who said that they're more advanced than we are, right? We could be more advanced than they are. But space is a very, very big place. This thing just happened to come by, unless it's an alien spaceship sent to check us out, which some people say. It just happened to go by in interstellar space. It happened to come near the sun, and then reflected by the sun, just swing around the sun. Space is a really, really, really big place. So the chance of just going through the solar system is small. So, but the point is that one did it, so that must mean others will do it again.
Yeah, 太空其实很大，那你不见得说别人就会科技超越我们，说不定我们科技超越别人的。但是呢，今天看到有一个刚好经过的太阳系绕出去以后，未来应该会有更多的。但太空就是很大，所以不容易发现这些东西。OK， 好，后面这位同学。
提到说这个发现来自太阳系外面的一些天体的这些部分，那我想请问说就是这些疯狂的天文物理学家们甘愿只做观察这件事吧？有没有一些计划去做一些更大胆的动作？除了观察以外，或者是说刚刚那个让一艘太空船经过这个木星，然后再经过太阳，然后增加它的速度，然后去贴到那个发现的这些天体上面，看能不能跟它做一个接近。那这个方法的可行度到底有多少之类的
？Yeah, he said that all these crazy astronomers are they going to do some more daring motions, like use a spacecraft going around the Earth and Sun and Jupiter, speed it up so they go parallel to 0.11 and to do close observation.
That was the idea when we talk about intercepting objects. So the point is, maybe we could use the sun to accelerate a spacecraft, to 30 kilometers a second. Then yes, then you can match the orbit of Muamua. So if you do it right, it's possible.
Yeah. 如果你真的是对那个重力加速做对的话，是可以达到每秒30公里。他所说的拦截，刚说很可惜没有早发现，早发现的话，拦截还真有可能的。经过几次绕了以后，速度达到一样，在旁边。说明 maybe you can see the alien brand on that。但是外星人摇摆的小标准。好，那其他旁边的同学。
我想跟他问的很像，就是我们可以利用一些类木行星那些大的星体来进行加速度。那我们人类有没有曾经利用这样的方法，然后抛射一些人造卫星到外太空去，让它脱离太阳系的这个，就是脱离太阳的重力范围。
Yeah, he's asking that if human beings have done it before to do gravity assist with all these Jewitt planets to go outward.
The idea is not new. The trouble is to get close to the sun without burning up. That's the problem, right? You have to get closer. The closer you get, the faster you're going to go. So in the case of that spacecraft, that's going to be solar wind. It's going to be I think 6 million kilometers from the surface of the sun. The problem there is how to not burn up. That is the hard part.
Yeah, 可以走很快经过太阳旁边 but he was asking about Jewitt planets. You can go Jewitt planets.
You can use Jupiter to do a gravity assist. You can do that, right? So it's all doable, but it's hard to go to Jupiter. That's why there's a reason why we keep going back to Mars, because it's easy. No, really. Because we keep sending spacecraft to Mars because it's easy. Going beyond Mars to Jupiter, it gets harder and harder. All kinds of technical problems, the radiation problem. So yes, you can go to the giant planets, but it just gets a lot harder.
Have we ever thrown a stellar light to out of solar system? Use a gravity assist.
Can we go out of the solar system?
Have we ever?
No, we have never sent us. Well, no, take it back. Voyager, the Voyager spacecraft are on their way out of the solar system. So yeah.
现在总共有4个，一个是先锋者 Pioneer 10, Pioneer 11, Voyager 1 and Voyager 2， 而 total 4 going out。但他们走了那么多年啊，先锋10号、11号刚刚走到太阳系的边缘，海王星它不是太阳系边缘，很里面的，它走太阳系边缘要走很久。航海家1号、2号还远着呢。那航海家1号去了木星的土星，2号去了木土天海，2号非常精彩，利用4个行星的那个 gravity assist， 刚好。那是刚好100年难得一见的排列，使得它可以走入4个行星，但是其他机会很少。Maybe that is Voyager 2, going around 4 planets really fast。然后经过3万年，航海家2号3万年以后，会孤单单的飞到金牛座的一颗恒星旁边。Maybe 3万年以后，那边的学生跑到河里面就看到一个外来的。Okay, any more questions? 哎，这边有个女同学哈。
This person, this lady, yes.
OK，麦克风交给他。
To ask that if we catch the this object, so what kind of measurement can we do? 就是在我们拦截到之后，我们可以对它做怎样的测量？
What kind of measurement can you do when you intercept?
A good picture would be very nice, right? So, because all the images we took, we didn't resolve the object. The object looked like a dot. right? We have no idea what shape they are. We know the shape only because of the brightness variation. So a good picture where you can see everything would be very good. Getting a sample would be very nice, but I think that would be very difficult because you have to match its velocity, get something, turn around, and come back to Earth. I think that's just probably just too hard. So one-way mission might be doable. Match the velocity, take pictures, send back, take as many measurements you can, take spectra, do everything you can. One-way mission would be good.
在这么早期阶段，你如果在旁边走着，然后拍一张很漂亮的照片，这就已经很精彩了。当然，他就说取样是更好。因为现在有一些方法，像日本的什么伊藤卡瓦那些的，他接近小行星以后，想办法撞一些东西起来，把它带过来，但你还要掉头回到地球上来。当你的速度走那么快，你想办法让这些东西锁过来是很困难的事情。但如果你有个sample很棒 ，Yeah, I would imagine. First one is a picture. Second one is a sample return. Third one is spacecraft landed on. Spacecraft. This is like a very beautiful runway. You landed upon it, and then doors open. Bruce Willis come out. 所以走出来最精彩了。Yeah. Okay. 还有别的继续问吗 ？Okay. 你要问吗 ？Okay. A question from another lady.
About the object is random to go into the solar system, or you can estimate by your mathematic ways to calculate maybe the overrates from other solar system and whole species.
Oh. So your question is, can we look at the orbit, go backward and figure out where it came from?
Right.
Theoretically, yes, but then the problem is this non-gravitational acceleration. If it were just gravity, sure, we know gravity very well. We can do math and we can find out where it came from. But there is non-gravitational acceleration, and that's completely random.
So we just can wait to see maybe the captain go again to cross our solar system.
Yes. So if there's non-gravitational acceleration, you can't go backward. You can't figure out where it came from because that part is random.
So that is very hard to estimate when the captain go into our solar system because you need to observe from early and early. So
right. But the trouble you can estimate, and estimating over a short period of time is okay. Because you estimate over a long period of time, then you get in trouble. But a short period of time estimation is okay.
Okay, thank you for this.
It's a very good question, Jane. Was the observation long enough to determine the non-gravitational acceleration constant or not?
The non-gravitational. That's why so they were able to. That's how they came up with the evidence that this thing had non-gravitational acceleration. It was the trajectory, right?
But can you trace back and determine if the non-gravitational acceleration remains the same even before?
Oh no, they can't go back that far. No.
所以你是没有办法决定它这个非重力的加速从开始到底有多少。所以你如果单纯是重力的话，Jane说了，科学家对重力一清二楚，倒回去推，你马上知道它从哪里来的。但现在多了一个非重力的加速，就没有办法决定它当初是哪里来的。所以
，Any other question?
还有其他问题
You guys can all have lunch with me if you want.
最后一个，李老师最后一个，last one.
我用中文问哈，就是他说的那个小行星的形状非常的长，轴非常的长，那有没有任何的猜测这个是怎么演变出来的？那在另外一个问题是，它的反射率如果改变了，那形状会不会也就跟着改变了？因为他猜测的是反射率10%。
Yeah, the estimate that is very elongated. 你刚刚问李老师，你说它的形状很长嘛，对不对？什么原因？问题是什么？它怎么样演化出来 ？How did it evolve?
How did something get to this?
If it's through natural evolution, you don't see that.
We have no idea. We have never seen anything in the solar system with this shape. Nothing. So there has never been anything with this kind of shape in the solar system. So we don't know how it got that way.
Yeah, and your observation is tumbled, so the variation changes a lot. But
no, the tumbling makes it the irregular, I would say. The variations are irregular. The counting doesn't change the elongation. Whether that elongation is there, whether it's counting or not.
它的那个长度在那个度是不会改变的。那the reflectivity remains the same, right? 是 assume to be.
The reflectivity, yes, we assume it's the same everywhere.
假设它的反射率是均匀的，然后不变的，所以是用这种方式。而它的宽轨是不规律的，转，所以你会看得到每一组 that's why every case has a different aspect ratio.
Because in the irregular, let me show you the picture. So this black line is what it should be if it's just regular rotation. But you can see the measurement don't fit exactly. So it's like this is good, this is good, this is not good, right? The predicted line is here and the measurements are here. So they don't repeat themselves very nicely. So that's
all these are 8-meter class telescopes.
These are all the world's biggest telescopes. So it's not like it's not. These are not wrong measurements.
OK， 那这不是错误的观测，这都是8米级望远镜，这都是正确的观测，但还是不规律的反馈。我觉得今天能够让Jane 能够跟大家讲这样的一个故事，而且是一个真实的新的发现，是很精彩的。Jane, so we conclude the talk.
Sure. You don't want to translate anymore.
Great. 就给大家一个热烈的鼓掌。You agree with me that this lady asked a very good question?
Yes, she deserves a book.
OK， 那越讲越好。OK， 好，那我们请编辑师院长来做。
合照一张好不好？